So let's take a look at the second part here of chapter one from our textbook. And we'll note here that this section is describing what we might know as the scientific method, or in general, this scientific approach to knowledge. And we can see some terms that are defined here. So observations are, what we can see, what we can smell, any type of bubbling that occurs, any type of color change. These are all different types of observations that can occur during experimentation. And if we're testing something, our hypothesis, we can do this through experimentation. A hypothesis is, in general, a question that we pose based on some observations that we might see. And we can note that observations can also be referred to as data. So anytime you collect either numeric data or non-numeric, qualitative or quantitative, so qualitative would be like yes or no type of answers, or color. So it went from red to blue. That would be qualitative data. And then we have our quantitative, which would be, okay, the temperature rose from 52 Celsius to 53 Celsius. That would be more of a quantitative, a quantity, a numeric value. So now that we know what observations are, we can formulate, after multiple observations, a hypothesis, right? We usually don't just see something one time and say, okay, we think this is why this happens, but over time, you see these observations, they can lead to what we call this hypothesis, this interpretation or explanation for our observations. And note that there's specific examples here given with Lavoisier. He, combusted a substance, phosphorus. He determined, when something burns, it will actually combine with oxygen, so a component of air. So actually, things were gaining mass after you were lighting them on fire. They kind of debunked this whole theory of phlogiston theory, which your textbook clearly doesn't mention because it's, more science fiction of the past, more of a history lesson of science and chemistry. But now we note that a hypothesis in general should be able to be falsifiable. So it has to be able to be disproven. So if you have this great hypothesis and there's no way that you can design an experiment to disprove it or falsify it, then it's not so good a hypothesis, because it's not so much that data will support your finding, it's that there's no way that we can disprove it, even if we were to do an experiment a million times. Falsifiable is a good thing in the world of hypotheses. So then we get to what is a scientific law. So this is after we do, multiple experimentations, have multiple observations, we can form a law. So this is kind of something that has the same kind of expectations are fulfilled every time we do this type of experiment. So we get to the point where we create a law. So conservation of mass. So as we noted with the Lavoisier experiment earlier, that we burned something and there should be this conservation of mass. So why were things getting heavier? Well, oxygen from the air, so O2 molecules were actually bonding with phosphorus, creating this oxide, this compound, and it was heavier than the starting material. So mass was conserved. This was proven after many, many experiments beyond Lavoisier's. But these laws will now allow us to predict future observations. So if we design a new experiment, these laws or guidelines will kind of help us to, predict the future, if you will, predict how things will react based on different manipulations. So Let's see here. So, unlike civil or governmental laws, they note you cannot choose to violate a scientific law. So, these are things that were bound by constraints of physics instead of just law, like legal laws. Let's see here. So, theory. After we have well-established hypotheses, we can form what's called a theory. This is a model that we create. So things like kinetic molecular theory, we'll learn about when we talk about gases. When gases move, we can talk about their motion in light of a theory. So again, after so many observations, a well-established hypothesis, which is the answer to these questions that we might pose from our observations, then we call this a theory. And again, we should note that experiments validate these theories. They support these theories. So here's some other examples. Here are another example, Dalton's atomic theory. So we still kind of follow this, right? We think of atoms as the building block of matter, the smallest, subatomic particles go down to protons, neutrons, electrons. But Dalton's atomic theory still holds true. And we use that to predict future observations, as noted here. So we can kind of follow this flow chart here to walk us through the scientific approach, the scientific method, where we start with some observations over here. We can form a hypothesis. We can also jump right to a law here. And what happens is these experiments, either we're just posing a question or we're saying that, these observations have happened so many times, we think it's already a law. The experimentation that we perform still needs to support our hypothesis, which would confirm the hypothesis, or we would revise it, test again, and then hope to confirm it again. The second time we do the experimentation, but our experiment should also confirm our law. Really, laws to be revised, usually they're kind of set in stone at this point, but it can be possible. Laws of gravitation, can be rewritten in the sense that Einstein has a theory of special relativity versus Newtonian mechanics. So quantum mechanics versus Newtonian mechanics sometimes argue, but still coexist. So after we have this hypothesis that has been confirmed time and time again, then we form our theory. But of course, we'll keep testing these theories and they can be revised as time goes on. So, what is the best explanation of the difference between a law and a theory? So we can see that a law will summarize our observations, our related observations, but our theory kind of explains or gives an underlying reason for them. So atomic theory describes everything as atoms, right? It gives us, okay, these observations of these different properties for different collections of things, which would be different numbers of subatomic particles, make an atom. So it gives us that whole reasoning behind our explanation. So we will stop here, and in our next video, we'll dive deeper into how to classify matter.